graduate student at Harvard University where I work with Avi Loeb, and today I'll be talking about how stellar tidal disruption flares can serve as useful signatures of black hole recoil, and in some cases, the gravitational wave emission that accompanies black hole coalescence as well. So over the course of this talk today, I'll begin with a quick review of the physics of stellar tidal disruption events, and then move on to how these events can be used as electromagnetic counterparts to gravitational wave signals, both prompt and relatively prompt, and then at the end I'll talk about how they can serve as an extremely delayed electromagnetic counterpart, maybe millions or billions of years after the signal itself, as a way to get an indicator of a recoiling supermassive black hole. There's one related topic that I won't be talking about today, and that's the tidal disruption of a neutron star. There are a few reasons for that. One is the time constraint, another is that that's not something to work on, and finally, that can only happen for a very low mass black hole that the neutron star is inspiraling into. So I don't think it would be of particular interest for a LISA or ELISA focused audience. Okay, so I'm going to begin by talking about the physics of tidal disruption events. And the basic picture to have in your mind is of a star living in a galactic nucleus on an orbit around a supermassive black hole. And something happens to the star, maybe a perturbation from a close encounter with another star, maybe something more complicated, but whatever the cause, the star is put on a low angular momentum trajectory that brings it within a certain distance or radius of the supermassive black hole. And in the simplest case of a Schwarzschild black hole, you can write this tidal disruption radius as just the radius of the star times the cube root of the black hole mass over the mass of the star. And interior to that radius, the tidal acceleration felt by fluid elements on the surface of the star will exceed the star's own gravitational acceleration, and it will be torn apart. And on this slide, I've included snapshots from two different hydrodynamical simulations of this process. One is from 1989, and I think might be the first simulation of it. Another is from 20 years later, and not too much has changed in the qualitative sense, although quantitatively things have obviously been refined quite a bit. And you can see the basic picture playing out here. A tidal bulge of order unity is raised on the star around the time it approaches its orbital pericenter. That tidal bulge is torqued by the black hole's gravitational field, and as a result of both overflowing, as a result of both the direct tidal forces and the spin up of the star disrupts. So when this happens, roughly 1/2 of the stellar mass is immediately unbound from the black hole, and of the remaining mass, it's put onto highly eccentric orbits with apocenters of maybe hundreds or thousands of gravitational radii. So just for comparison's sake, if you have a 10 to the 6 solar mass black hole, the tidal radius is more like 50 m. And one important thing to notice here that'll be important later in the talk as well is that because the tidal radius scales with the cube root of the black hole mass, and the Schwarzschild radius scales linearly with the black hole mass, for any particular star, there's sort of a maximally massive black hole that can disrupt it. And for main sequence stars, that mass is about 10 to the 8 solar masses. So above 10 to the 8 solar masses, the black hole can't disrupt a main sequence star. So this disrupted debris is put on bound very eccentric orbits, but when these orbits, and as these orbits move away from the black hole, they're basically following geodesics. But as they return to the black hole and funnel together on their first pericenter passage, they begin to collisionally shock with each other and dissipate energy. And this dissipation of energy allows an accretion disk to form. And over the weeks to months following the disruption event, this disk will radiate very heavily in the ultraviolet and X-ray part of the spectrum, and with luminosities comparable to a supernova. And in principle, this emission has some very useful features that can distinguish it from other types of variability that you would see in the galactic nucleus. Probably the most commonly known one of these features is this t to the negative 5/3 decay rate in the rate at which mass returns to the black hole. Although there are others that I can talk about if people are curious afterwards. And one final thing I'll note about this process is that if your black hole mass is below 10 to the 7 solar masses, the initial rate of mass return will be above the Eddington limit, and for 10 to the 6 solar mass black holes, quite a bit above the Eddington limit, maybe a factor of a few to a 10. So the dynamics of this period are relatively uncertain, but many of the models that have been produced, many of the theoretical models that have been produced for this, anticipate very high levels of optical luminosity that can aid in the detection of these flares. So these aren't just things that theorists dream up to satisfy themselves. there's relatively strong observational evidence that tidal disruption flares exist in the universe. So far, they're of order 10, probably a few more strong candidates, most of which were detected in the X-ray or ultraviolet part of the spectrum. But over the last few years, people have been making optical detections as well, both with time-domain optical instruments like the Pau Amaro-Seoane Factory and in archival SDSF searches. So in these graphs off to the right, I've included some pictures of 3 different candidate events found by the ultraviolet Galax satellite. And on the left column, we have the light curve, so the evolution of the luminosity versus time. And these solid lines here and here are t to the negative 5/3 power laws drawn in by hand. The dotted lines are fits to the data at later times, after about a year or so, when there seem to be significant deviations from that t to the negative 5/3 law. But at early times, at least, it seems to fit the data reasonably well. And on the right-hand side, we have the SEDs for these events, which also seem to fit pretty well, just the simplest multicolor black body model for an accretion disk people can come up with. And although we haven't seen too many of these so far, the advent of time domain surveys, in particular LSST, are expected to increase our sample size of tidal disruption flares by orders of magnitude, maybe allowing us to see tens to thousands, depending on the details of the super Eddington state of accretion every year. So, okay, so why should general relativists and an audience that's focused on gravitational waves care about this? The reason is that these events, because they only happen in the presence of a massive black hole, can serve as useful electromagnetic counterparts to gravitational wave emission. And one example of this is the in-spiral of a white dwarf into an intermediate mass black hole. And I emphasize here the intermediate mass part of the black hole, and that's because for something as compact as a white dwarf, you need a black hole with a mass less than about 2 times 10 to the 5 solar masses, modulo a factor of a few of the black holes spinning, in order to actually disrupt the white dwarf. Otherwise, if you have a heavier black hole, the white dwarf will just be swallowed whole without emitting any interesting electromagnetic signal. And there are a couple of different ways in which this in-spiral can happen, or rather this disruption can happen. And they've been investigated recently. I think there was a 2008 paper by Sasana et al., as well as a more recent one by Clausen and Heraclitus. And in both of these papers, they sort of looked at a standard tidal disruption scenario where you have a variant on the physical picture I gave you for the disruption of a main sequence star. The difference is that for a more compact object like the white dwarf, I mean, certain things scale differently. The time scales are all shorter, etc. And this scenario you would expect to be reasonable if you have a white dwarf whose orbit is directly scattered into the tidal sphere. The one interesting twist on this that doesn't happen for main sequence stars is that if it's scattered very deeply into the tidal sphere, then the enormous compression that the white dwarf undergoes before it disrupts could lead to a thermonuclear detonation, which would look kind of like a strange type 1a supernova. There's another scenario which was proposed more recently by Zalamea and Manu and collaborators, which looks at the case of a very slow, more gentle in-spiral into I think a heavier ion BH. And in this case, you have what looks more like stable mass transfer through an overflowing Roche lobe. So in this case, you could potentially have a coincident gravitational wave and EM signal lasting days to weeks. So these are exciting things to think about if you believe in ion BHs. So now I'm going to talk a little more about how tidal disruption flares can accompany gravitational wave signals from supermassive black holes, and this gets more into my own research. So Avi and I put out a paper last year about how the gravitational wave recoil imparted to a merged black hole can create an instantaneous, or not instantaneous, but can create a burst of stellar tidal disruptions rapidly after the recoil event. And to explain why this works, I'm going to have to talk a little about how rates of tidal disruption are set in normal galaxies. And the way this is often thought of is by considering the population of stars as satisfying some distribution function f with regard to the x and v coordinates in a 6-dimensional phase space around the supermassive black hole. And in that phase space, there'll be a region called the loss cone, in which stellar orbits have very low values of angular momentum, and upon completion of one orbit, they would be disrupted. So I'm simplifying things a little here, but for most of that loss cone, in particular the region with semi-major axes close to the black hole, you expect that lost cone to be pretty devoid of stars. Any star that lived there would have been disrupted a long time ago. And you can visualize this with this diagram here taken from a Merritt and Milos-Aboueva's paper from 2003. So in this diagram we have a spherically symmetric galaxy. So instead of having a 6D phase space, we have a 2D phase space. The stellar orbits can be classified by their specific energy and their specific angular momentum. So in the unit convention we've chosen here, the more tightly bound orbits have higher values of energy. So we're really looking at the absolute value of the Newtonian potential energy. And then this j-axis right here just depicts the normalized angular momentum. So the angular momentum of the star divided by the angular momentum for an equivalent circular orbit. So the outer edge of the phase space has a j value equal to 1, and lower values of j have lower pericenters compared to other stars with their semi-major axis. And this funnel-shaped region right here is the lost cone. You expect it to be empty of stars, but the region out here you expect to be populated by stars. And there's a very simple analytic expression for the shape of the lost cone in phase space. Now, when you consider a normal galaxy with a stationary supermassive black hole in the center, the rate of tidal disruption will be set by the rate at which stars from the occupied region of phase space can diffuse or relax into this lost cone. And when they enter, they drain on they get disrupted on a dynamical timescale. But what happens if you have a recoiling supermassive black hole? So if some kind of kick is imparted to your supermassive black hole on a timescale that appears instantaneous to slower stellar orbits, as is the case with gravitational wave recoil, then this phase space lost cone will be tilted. So the equation for the lost cone becomes different, and it tilts or shifts into a non-empty region of phase space. So a portion of the lost cone instantaneously refills, and the stars that now live in the new lost cone will drain out on a dynamical timescale. And in order to calculate the rate of tidal disruptions and the number of tidal disruptions from this refilled lost cone, all you need to do is calculate an overlap integral. And let's see, I guess that in a few slides from now, I'll refer to the old lost cone as the LC, and the new lost cone as the LC prime. So I want to introduce that notation now. And the important thing to note here is just that the orbital timescales for stars this close to a black hole are orders of magnitude less than relaxational timescales. So this can increase the tidal disruption rate quite dramatically. In a normal galaxy, you expect maybe 10 to the negative 4 to 10 to the negative 6 disruptions per year. That can increase to of the order 1 disruption every 10 years or maybe even higher. So the tricky part of this is figuring out what the right distribution function is to use for your stars, because you're not dealing with a normal galaxy, you're dealing with a galaxy that has just finished passing through the final stages of supermassive black hole in spiral. So it turns out that the distribution function you use is going to be very sensitive to how you solve the final parsec problem. And for most of this talk, I'll be talking about dry merger solutions to the final parsec problem, just because those are more tractable analytically, and that's most of what Avi and I dealt with in this paper. So two plausible solutions are nuclear triaxiality and collisional relaxation. So if the geometry of your stellar potential in your nucleus is significantly triaxial, then a subpopulation of stars in the galactic nucleus will have centrophilic orbits that take them arbitrarily close to the black hole, or the black hole binary back when it's a binary. And because of that just gives you a very large supply of stars to scatter off the supermassive black hole binary and steal its angular momentum. So you can coalesce a binary pretty quickly that way. A different way to do it that's often slower but works even if you don't have a triaxiality to your galactic nucleus is collisional relaxation. So very quickly the binary black hole will scour out all the stars that are likely to be fed into its blender. That's why the black hole binary stalls. That's the origin of the final parsec problem in dry mergers. But stars will have two-body encounters with each other and relax into the binary lost cone. This process is only effective in less than Hubble time if the mass of the black hole is under about 10 to the 7 solar masses. So the basic difference between these two solutions is that the triaxiality solution produces a very shallow, lower density stellar core around the black hole binary, whereas collisional relaxation produces this kind of joint core cusp profile with a shallow core on the outside steepening to to a sharper cusp and higher stellar densities. So I set up my distribution functions by taking those two density profiles, but I have to carve out a binary loss cone. So I have to remove by hand all of the stars from the distribution function that would have been eliminated by the final stages of the binary coalescence. And the way I do that is by calculating two decoupling radii. So the first decoupling radius occurs when the rate of change of the black hole binary's semi-major axis from stellar scatterings falls below the rate of change of its semi-major axis from gravitational wave emission. So at that point, two-body relaxation becomes inefficient at scattering stars further inward, and you don't have any stars with semi-major axes less than this decoupling radius. But relaxation in angular momentum space is faster than relaxation in energy space, so there's a second interior decoupling radius, interior of which there can be no stars at all. So inside this outer decoupling radius, there are no orbits with semi-major axes within this radius. But orbits can have semi-major axes greater than this radius and pericenters that land inside. They can't have pericenters that enter this second decoupling radius here. So those are the cuts I make to bring my distribution function in line with a binary loss cone. So what are the results I get from this? What are the calculations of my overlap integral? The two physical scenarios I consider are these green and blue lines. The difference between them isn't terribly important. And on the y-axis here, I plotted the number of disruption events within 100 years of the black hole merger, and you can see that there aren't a ton, maybe 2 or 3 for these two sweet spots. So there's a sweet spot in black hole mass between 10 to the 6 and 10 to the 7 solar masses, and there's a sweet spot in kick velocities as well between about 200 and 1,000 kilometers per second. At high masses, your problem is that all of the stars that are in the new refilled loss cone have very long orbital periods longer than 100 years. At low masses, the problem is that there just aren't that many stars. At low kick velocities, the problem is that there's a lot of overlap between the new and the old loss cone, so there's very little refilling that's done. And at high kick velocities, the problem is that there just aren't very many stars that remain bound to the kick black hole. This black line doesn't represent a physical scenario, but it represents an important point that I'm going to talk about later to discuss why I think these estimates are conservative. So this black line right here is what happens if you don't remove the stars from the binary loss cone. And the key point is that the number of stars you remove for stellar masses below about 10 to the 7 solar masses is very small, on order of dozens. So if there's some other process, I'll talk about this in a minute, that could resupply stars interior to the decoupling radii I talked about, just a handful of stars, then you could see elevated rates here. The other thing worth noting is that these are expected values for the number of stars to be disrupted within 100 years, and particularly at low masses, the expected value for stellar disruptions within a more reasonable time scale, like 5 or 10 years, doesn't go to 0. It goes to maybe 0.3. So about roughly a third of 10 to the 6 solar mass black holes that are kicked with velocities within this range will see a tidal disruption within 5 or 10 years or so, a more reasonable number than the 20 or 30 that you expect for heavier black holes. There are other considerations also which could enhance this rate. I've neglected discussing web mergers, although I talk about this a little in the paper. And the basic idea here is what Monica touched on earlier. Just the process of a web merger can rebuild a steep stellar cusp. And to be more specific about how the physical processes going on in web mergers could repopulate the binary loss cone, it's been known for a while that in the presence of a thick accretion disk, stars whose orbits intersect the disk can be captured into the disk and then begin type 1 or type 2 migration, depending on the disk parameters. So in that way, the real decoupling radius could be something interior to the ones I've talked about. It could instead be the radius at which basically the viscous time scale is equal to the gravitational wave coalescence time scale. The other possibility that could enhance this rate to higher levels is if resonant migration in dry mergers is capable of bringing in extra stars into the refilled loss cone region, and like I illustrated with that black line, you really only need to migrate on order of tens of stars. And this has already been demonstrated for the special case of the one-to-one resonance by Cito and Muto in a 2010 paper, and then Jeremy Schnittman in another. So Avi and I are currently looking into higher order mean motion resonances, and we don't have a result yet, but there's, I would say, definitely a good chance that this could enhance the rates to higher levels. So I'm running out of time, so I'm just going to talk very quickly about this second project that Avi and I have completed this year, which is a delayed signal. So millions or billions of years after a supermassive black hole is ejected out of its galactic nucleus, it can be wandering through its host galaxy and will have the ability to produce spatially offset tidal disruption flares. I'm going to have to skip through a few slides here, but the basic idea is that there are two types of stars that can be disrupted by a wandering black hole: stars that remain gravitationally bound to it, and the random stars that it encounters as it wanders through the galaxy. And if it disrupts stars from either of these classes, it can produce a stellar tidal disruption with an observable spatial offset from the center of its galaxy, which isn't something you expect many other scenarios to produce. I think the only real source of confusion, which would be something like an infalling satellite galaxy, can be distinguished from this, and I can talk about that more in questions. But so in order to, I'm sorry, I should say that this scenario was first proposed by Camosa and Merritt in a 2008 paper, but they limited themselves to discussing the small percent of astrophysical kicks where the kick velocity is greater than the galactic escape velocity. So in these cases, they're very exciting. You could have an intergalactic tidal disruption flare, but if you generalize this scenario to more realistic distributions of kick velocities, and in this paper we used the Lusto et al. 2010 distributions for wet and dry mergers, then we can come up with an actual rate estimate for what a time domain survey like LSST might be expected to see. So in order to do this, we mocked up, we made up a semi-analytic model for the evolution of these trajectories so that we could explore as much parameter space as possible, much more than if we had done actual numerical simulations. And we set up a mock galaxy catalog based on the Nuker team's observations of bulges in the nearby universe, so based on the Lauer et al. 2005 paper. And we modeled tens of thousands of trajectories for different kick velocities, different sets of galaxy parameters, different spin distributions, and then integrated over the distribution functions we had put together for all of these things to calculate the expected number of spatially offset tidal disruption events that LSST will see every year. And I don't have time to talk about too many of the details, so I'll skip to the final result right here. So we basically considered, I guess, 6 models. So in 3 of the models, we included super Eddington outflows, which dramatically increased the optical luminosity. In the other 3 models, we were more conservative and considered only the case of more theoretically secure disk emission. And then we also split the models down by the kick velocity distribution we used. So in 2 of the models, we assumed initial spins that were completely unaligned, or aligned to within 180 degrees. In 2, we considered spins aligned to within 30 degrees, and in 2, we considered spins aligned to within 10 degrees. And the takeaway number here is this. So gamma S is the number of tidal disruption flares that LSST will see automatically through photometric subtraction without any follow-up whatsoever every year. And this number in front is from the fiducial spin distribution. And you can see that for all of our models, except the most pessimistic one, highly aligned spins and no super Eddington outflows, LSST will automatically see an interesting number of these spatially offset flares per year, which could serve as a unique signature of black hole recoil. The remaining challenge is classifying these transients, and that's a question for another day. But the signal is there if we can find an efficient way to pick it out. So that I'm going to wrap up and just say that just summarize by saying that I think there are a variety of ways in which flares from tidally disrupted stars can provide interesting signatures of gravitational wave emission or evidence for processes involved in that, like gravitational wave recoil. Thank you for your time.